Miscellaneous exercise 5. I'll go to question number 3. Differentiate this function 5x raised to 3 cos 2x. Now you must have realized this like variable raised to variable form. Variable raised to variable form. So you need to use logarithmic function to differentiate this. So let me call this as, for example, y equals to 5x the whole raised to 3 times cos 2x. Now the easiest way is you just apply log on both the sides here. So applying log, so log of y equals to here log of 5x the whole raised to 3 times cos 2x. This is just because of applying log, applying log function here, right? Now you know this property, this power will be in the product here. So here this will be in the product. So therefore log y equals to 3 times cosine 2x into log of 5x. Which property I have used here? Log of x raised to n equals to n log x. This you know. Okay. Now we just differentiate this. This is like an implicit function. So differentiating with respect to x here. We just differentiate with respect to x here. What is derivative of log y? You know, 1 upon y into dy by dx. Chain rule. This you know very well. Log y, you imagine this as x. So 1 upon x into dy by dx by chain rule. Here product rule. 3 as it is. Differentiation of cos 2x, which is minus sine 2x into 2 by chain rule. Log of 5x as it is. Plus now here 3 times cos 2x as it is, 3 being constant as it is. We already differentiated cos function, so now this one as it is into differentiation of this portion. Imagine this as x, so 1 upon 5x into by chain rule derivative of 5x is just 5 here. So finally dy by dx equals to, I'll take y on this side, this is minus 6 sine 2x into log of 5x. Here 5 will get cancelled, plus you have 3 times cos 2x the whole by x. This is final dy by dx. If you want, you can just put the value of phi here. So dy by dx equals to, what was y? Just look at here. It is 5x the whole raised to 3 times cos 2x into, you just copy this expression. This is required dy by dx. Question number 6. This is an important example here. You are given cot inverse this expression. So let me call this as y, for example. We are given y equals to this. So we get the dy by dx. You know, in such questions you need to simplify in your expression. You cannot use blindly chain rule, remember. And we try to get the cot inside this bracket. So cot inverse and cot will get cancelled. Now you recall, 1 plus sine x. If you remember, instead of 1 you can write, for example, cos square x by 2 plus sine square x by 2. And what's this? Half angle formula, 2 sine x by 2 into cos x by 2. This one you know very well from 11th standard rego. So this becomes perfect square. Cos x by 2 plus sine x by 2 the whole square. And same way here, therefore we have this, and same way if you find 1 minus sine x, it would be just cosine x by 2 minus sine x by 2 the whole square. Same procedure. So we have this too. Fine. Now we take the square root here. So therefore if I take the square root, on the right hand side you have modulus. This one you know very well. What is root of x square? It's a modulus x. This you know. So here your modulus cosine x by 2 plus sine x by 2. But here x by 2 is from 0 to pi by 4, remember. So it will be in the first quadrant. So this is positive. So modulus x will be just x. And root of 1 minus sine x, it would be again cos x by 2 minus sine x by 2. Why? Because in 0 to pi by 4, cos x is always greater than sine x, remember. In 0 to pi by 4, this is always true. You just look at a graph, you will realize. If you want, just you see here. If I see the graph, 0, this is pi by 2. This is a graph of sine function, 0 to pi by 2. And here graph starts from here for cos function like this. This is pi by 4. So here at pi by 4, you see the value of cos function is bigger than the sine function. This is sine function. This is cos function. So cos x is always greater than sine x. So this is positive, and that's why I dropped the modulus. Now we place both these values there. So you are almost through. This is the only important part. Y equals to cot inverse. Here, this is cosine x by 2 plus sine x by 2 plus cos x by 2 minus sine x by 2 upon cos x by 2 plus sine x by 2 minus here cos x by 2 plus sine x by 2. So now you see inside the bracket here. Inside the bracket, if you look at, you are just left with cot function. Why? Because this sine will get cancelled. This is twice cos x by 2. This cos will get cancelled. This is twice sine x by 2. So this is cot inverse cot x by 2. Y equals to this. Now you know that the domain of cot function or cot inverse is 0 to pi, if you remember, right? There is a domain of cot function 0, open 0 to open pi, and here you have 0 to pi by 2. So you can cancel this 2. So therefore y equals to cot, this is just x by 2. So this portion is nothing but this is our inverse trigo chapter. Chapter number 2, remember. This is not differentiation. Now differentiation would be just one line. Therefore, dy by dx equals to here 2 being constant, derivative of x with respect to x is 1. So important portion is second chapter, inverse trigo functions. Next question, 7th number. You have log x. This is a variable, this is a variable. This is a variable raised to variable form. Let me take this as a function, for example, y here. So let's take y equals to this. Now if you remember, differentiation of x raised to x. What is that? X raised to x into 1 plus log x. This is like standard formula. Here one way to do this question is you can apply log on both the sides. So applying log on both the sides. Applying log on both the sides, and you can proceed further. Right? This is one way. But in MCQs, you can do like this. What you can do is, here you have y equals to log x raised to log x. So this looks like x raised to x. You imagine this as x. X raised to x. What's the derivative of x raised to x? X raised to x 1 plus log x. So how do I rewrite here? X raised to x. So log x raised to log x into, inside the bracket, 1 plus log of x. But what is your x? X is also log x here. I've just copied this, but instead of x here everywhere, you have here log x, remember. So log x raised to log x, inside the bracket 1 plus log of, instead of x I wrote log x. Now recall the chain rule. Which one you had considered as x? That is log x. So by chain rule, d by dx of log x. This is by chain rule, remember, because you had considered log x as x. So finally, you know derivative of this one is just 1 by x. So I'll take that over here. Log x raised to log x upon x into 1 plus log of log x. This is dy by dx. Right? In MCQs you can use this. In subjective, if it is asked, this should not be used. I just wanted to show you by that MCQs method. Even if you look at the 9th question, same procedure here. You have sin x minus cos x, the whole raised to sin x minus cos x. So you can do the same way. You see here, this looks like x raised to x. And you know differentiation of x raised to x. So here, dy by dx, if I write directly, x raised to x, x raised to x, into inside the bracket 1 plus log of x, 1 plus log of x. But what is your x? That is sin x minus cos x, into here, into by chain rule d by dx of considered x. Which one you had considered x? Sin x minus cos x. So you know differentiation of this, so you'll get the final derivative. This is just for your information. In MCQs you can do like this directly. Here you need to write the derivative, so you'll get the final answer. Okay, we'll go to question number 10 here. 10th question. Question number 10, you are given here x raised to x, x raised to a, plus a raised to x, plus a raised to a. Remember here a and x both are greater than 0. Fine. Now here there are 4 functions, 1, 2, 3 and 4. You must have noticed that this is a constant, so derivative is 0. A raised to x, you know that is a standard function. What's the derivative of a raised to x? A raised to x into log a, exponent. This is power function, x raised to 3, x raised to 4 and so on. And this is very well known standard function, you know differentiation. So what you need to do, you need to take this as a separate function here. Let's take y equals to this. I'll take this as u here, because this variable raised to variable you need to find separately. You cannot apply log like this. If you write like this is wrong, remember. Log y equals to log of x raised to x plus x raised to a plus a raised to x plus a raised to a. And if I take log inside, this is wrong. This cannot be done. Log should be applied only when you have product. So this should not be done. This should not be done here, remember. So I'll take this separately. Let's take u equals to x raised to x. And I'll find du by dx. You know how to do this. I'm writing directly here. X raised to x into 1 plus log x. You need to do this, remember. Full method I have written directly. So therefore now here y equals to u plus x raised to a plus a raised to x plus a raised to a. Why no need to take v and so on here? Because this is very standard function, you know derivative. Standard function, you know derivative. Standard function, you know derivative. So therefore you can do directly. Therefore dy by dx equals to du by dx plus derivative of x raised to a into x raised to a minus 1. This is a power function, remember. How do you differentiate x raised to 3? You imagine this is like x raised to 4, for example. 4x cube. How do you differentiate x raised to 4? 4x cube. So how do you differentiate x raised to a x raised to 1 less power, a minus 1. That's what I've written here. Fine. Plus, this is a standard exponential function, a raised to x into log a. You can see that there is no variable, constant, so derivative is 0 here. So finally, if I place the value of du by dx here, what is that? This one. So x raised to x into 1 plus log x plus a into x raised to a minus 1 plus a raised to x into log a. This is your required dy by dx. This is dy by dx if y is the given function. Okay. Now next question number 11. If I just go for 11th question here. So here you can see that you have variable raised to variable form, variable raised to variable form. Let me call this as a function y here. Y equals to this. Now you have addition on the right hand side, remember. So you cannot apply log on both the sides. So how we'll do? We take this as u. Take u equals to x raised to x squared minus 3. Why we need to do like this? This is because this is a variable raised to variable form. And I'll take another function v equals to x minus 3 the whole square, here x squared. So now we apply the log, you get the du by dx. We apply the log, we get the dv by dx. That's the derivative with respect to x. But before we do that, here y becomes what it would be, u plus v. Call this as 1. Okay. Now we just, you know this, I think. Now you can do it. I'll just do for one part, applying log here. So log u equals to log of x raised to x squared minus 3. Now that x will be in x squared minus 3, this will be in the product, you know now. So log u equals to x squared minus 3 into log x. Now we differentiate this. So differentiating with respect to x. How do we differentiate log u? Imagine this as x. So 1 upon x into du by dx. 1 upon u into du by dx equals to, here product rule, x squared minus 3 as it is. What's the derivative of log x? 1 upon x. Plus here log x as it is. What's the derivative of this portion? 2x. Product rule on the right hand side, remember. I repeat this. Derivative of log u. Imagine this as x. Derivative of log x is 1 upon x. By chain rule, derivative of u with respect to x du by dx. This one as it is. Derivative of log x is this. Plus log x as it is. Derivative of this portion is this one. So therefore du by dx equals to, finally, du by dx equals to, u will move this side. But what is u? I'll place that directly. So x raised to x squared minus 3 into x squared minus 3 by x plus log x into 2x. Du by dx equals to, u will move this side. What is u? That is this portion which are placed here. Inside the bracket, this one as it is. In same way, get the dv by dx. You find as I did this. And therefore, from now, if I write from 1 dy by dx, I'm differentiating 1. 1 is here. Dy by dx equals to du by dx plus dv by dx. And now you just put the values of both. Du by dx is here, you place here, plus you same way place the value of dv by dx. We had many such questions earlier. Question number 14, you are given here x into root 1 plus y into root 1 plus x, and you want to prove dy by dx equals to something. Now you must have realized this is called implicit function, an equation about both the variables. So you can differentiate it directly. You can do this also, differentiating with respect to x directly, and you just get the dy by dx. That is one way. But instead of this, here on one side you have zeros, I'll simplify. Or this is another way of doing the same question. What I'll do, I'll take this one over there and I'll square it. So x squared into 1 plus y equals to y squared into 1 plus x. What I did, taking this expression over there and then squaring, by squaring, remember here. I've squared on both the sides. Now here x square plus x square y equals to y square plus y square x. Question number 23. You are given y equals to e raised to this, and you want to prove that 1 minus x square into y2 means d square by dx square, minus x y1 means dy by dx, minus a square y equals to 0. You want to prove this. Okay, so we just differentiate it twice. This is again good example. So I'll start with this. I'll write y1. y1 means differentiating with respect to x, remember. Okay, so how will differentiate on the right hand side? Imagine this is x. What is derivative of e raised to x? You know it is e raised to x into d by dx of a cos inverse x. So therefore y1 equals to this is e raised to a cos inverse x as it is into here differentiation. A being constant as it is, differentiation of cos inverse x minus 1 upon root of 1 minus x squared. You know this. Now usually in this double derivative questions, as I told you earlier, before you go for y2 you simplify this little bit. So I'll take this one over here. This is minus a. Now this is nothing but actually you see that is just y. Call this as 1 for example. So this is y because of 1. Okay. Now if you here into y1 is there. Now if you look at the required expression, somewhere we want a square and we want without square root. So I'll square this before I differentiate it twice. Squaring. So what I'll get? y1 squared into 1 minus x squared equals to a squared y squared. Now we differentiate it. So now again differentiating, remember. So differentiating with respect to x. So on the left hand side, product rule, remember, y1 squared as it is. What's the differentiation of this portion? Minus 2x. 1, 0, this is minus 2x. Plus, now 1 minus x squared as it is. What is this? This is by chain rule. Imagine this as x. So 2y1 into, this is differentiation of y1 which is y2. I repeat this portion. We did it earlier if you remember. What's the derivative of y squared? By chain rule 2y into dy by dx which is y1. What is derivative of y1 square? Imagine this as x. 2 y1, this is like x square, into differentiation of y1 which is y2. I already explained this earlier. So we have this here, remember. Equals to a square being constant as it is, and differentiation of y square as I explained here, 2y y1. Now you can so differentiation is over. You notice that there is something common, that is dividing by 2y1. So here minus x, 2 will goes away, y1 plus you are dividing by this portion. So 1 minus x squared into y2. 2y1 will goes away, so you are left with a square y. So therefore finally 1 minus x squared into y2 minus x y1 minus a square y equals to 0. Proved. It's a good example here.